Okay, for part C, I'm going to go ahead and switch again to writing sine of u as just s, and then cosine as just c. So as I do for part C, I'm going to do certain things like, for example, 1 plus s over s is fine. But when I have something like cotangent of u minus cosine of u all over cosine of u, what I'll do is replace the cotangent in terms of c and s as well, just so that it makes it have common functions throughout, rather than having three functions, sine, cosine, and cotangent. We'll just have sine and cosine to deal with. So cotangent is c over s, and then cosine is c, and then that's all over c. So one thing that I notice is that we have multiple fractions here. So common denominator would be s times c. So LCD is s times c. So when we multiply the first fraction by s times c to force it to have an LCD of s times c, that would mean I would have to multiply the top and the bottom by c over c, and that's going to give us the sc on the bottom, as opposed to the second fraction is missing. The second fraction here is missing the s, so I'm going to multiply top and bottom by s, and that's going to give me sc on the bottom for both. So let's go ahead and rewrite that as c times 1 plus s. That's on the left side of my fraction. I'm going to take the plus sign, put it in between. Now we're going to have a single fraction all over sc. And then the right hand side, you guys have c over s minus c times that quantity times s. Well, what we can do is take and distribute the s to each one of these terms inside the parentheses, and find that the s will cancel out with the first fraction, so you have just c left, and then minus sc. Okay, we can simplify this further. This is just an expression. If I distribute, I get c plus cs plus c minus sc all over sc. Well, c and c is 2c, and then cs minus cs will cancel out. Remember that multiplication is commutative, so sc and cs are the same thing, all over sc. And then again, our c's cancel out, so we're left with 2 over sine of, want to keep it consistent, we use u as a variable. For question D, it asks us to simplify an expression that has sine squared sine squared of v minus 1, which you'll notice is a difference of squares. So what we're going to do is factor the top and then see what we can do to factor the bottom. So factoring the top, we get sine minus 1 times sine plus 1, difference of squares, over, you'll notice that tangent is in both terms on the bottom, so that's the GCF. Tangent of v we can factor out. We get sine minus 1 left. So sine minus 1 is a factor on top, it's a factor on the bottom, so we can reduce that, and our final answer is sine of the angle v plus 1 all over tangent. So we're going to go ahead and add another example of verifying an identity. So when we have an identity, it's an equation, as opposed to simplifying, like number 4 is an expression. So when we verify an identity, we're trying to show that one side is equal to the other side. So we pick one side to begin with. This looks fairly equal in complexity on the left and the right. So I'm just going to pick the left to start with, and we're trying to show that the left is equal to the right. So when I'm starting with tangent squared and sine squared, one thing I can do to simplify is the guideline that was established is you can use and rewrite things in terms of sine and cosine. So number 3. So sometimes if it's not clear to you at first, you can switch everything to sine and cosine. So for example, tangent squared is sine squared over cosine squared. Minus sine squared is s squared. And then we're trying to show that that's equal to tangent squared of theta, and this side I'm not going to abbreviate, times sine squared of theta. So now I'm just going to work on the left. On the left, now that I switched that over, I have a fraction. So within the fraction, I can find the common denominator. So if I put 1 over that, the common denominator would be c squared. So that means I would multiply the second fraction by c squared over c squared to force it to have the same denominator. That's now going to get me s squared minus s squared times c squared all over c squared all over c squared, my common denominator. Okay, on top, I noticed that s squared is in both terms, in the first term and in the second term, so I can factor out s squared. Get 1 minus c squared all over c squared. Okay, so 1 minus c squared should look familiar to you. That's the Pythagorean identity for s squared. And then s squared over c squared, well, we began with that. S squared over c squared is tangent squared. So let me highlight two things. Sine squared over c squared could be rewritten so that s squared over c squared is one fraction. And the other fraction is 1 minus c squared, and 1 minus c squared, we are going to replace that with, that's the Pythagorean identity for sine squared of theta. So if I replace that with sine squared, I have s squared here. So s squared over c squared, remember, was equivalent to tangent squared. So tangent squared of theta times sine squared of theta, and that is exactly what we were trying to show. That the left-hand side, tangent squared of theta minus sine squared of theta, is equal to tangent squared times sine squared. So write the last step where you're showing that the left is equal to the right, and you verified the identity.